Okay, so I'd like to discuss detail of the heterotic tree construction today. But let me just first remind you about the general thing about symmetry. And in particular, the special feature in two-dimensional conformal field theory, which is the following. So there is, in general, there is a thing called Noether theorem. So if G is a Lie algebra, so Lie group, excuse me, and then there is a corresponding Lie algebra. And then suppose there is a symmetry, the quantum theory has a symmetry with respect to this Lie group. And then there is a thing called Wigner theorem that says that this Lie group action can be implemented as a unitary operator on the Hilbert space. And so Wigner theorem says that the G acts unitarily on the Hilbert space. So that means that Hilbert space can be decomposed into some of the reducible representation of the group. And Noether theorem says that you can implement, you can realize this unitary group action in terms of group element. So if you have a Lie algebra, there is a generator of Lie algebra. And since exponential of this Lie algebra generator generate Lie group, which acts unitarily on the Hilbert space, so that means that Q is realized as a Hermitian operator on the Hilbert space. So QA is a Hermitian on the Hilbert space. And the Noether theorem says that there is some kind of current. So in general, in d-dimensional quantum field theory, there is a vector current, which is conserved. And Q of A is expressed as integral over Cauchy slice of the time component of A. Okay, so this is what Noether theorem says. So let's apply that to 2D CFT. So in 2D CFT, so what this means is that there must be a current which now has two components, the holomorphic and anti-holomorphic component, and it must satisfy this equation because it should be conserved. Okay? But there is a special feature of two-dimensional CFT, which is the following. So if you calculate H and H bar for J, Z, well, it's a one form with respect to Z. And so H and H bar for this operator should be 1, 0. And similarly, for this operator, it should be 0, 1. Okay? So now, this already tells you something very interesting, which is the following. So there is a state operator correspondence in CFT. So that means that there must be a state corresponding to this operator. Acting on the vacuum state, and this state has conformal dimension 1, 0, just like this operator, which means that you have an action of Virasoro algebra. There is an action of Virasoro operator such that Ln annihilate for all n greater than 1, and L0 of A is H, which is equal to 1. And similarly, Ln bar annihilates this. And L0 bar A also annihilated because the conformal dimension of H bar is equal to 0. Now this means, in particular, this means something very special. Because L1, L minus 1, well here we are considering bar, is equal to twice of L0 bar by the Virasoro commutation relations. So if you sandwich this with respect to this operator, or with respect to this state, then this is equal to twice of A, L0 bar A. But this by definition vanishes because A is a state that is that corresponds to this current which has conformal dimension 1, 0. But A gets annihilated by L1, so that means that this is equal to A, L1 bar, L minus 1 bar A. Namely, this is a norm square of L minus 1 bar A. So therefore, if the Hilbert space has positive definite inner product, the state which has 0 norm, like this, has to be 0 by itself. So that means that it implies that L minus 1 acting on A has to vanish, which if you bring it up by to state operator correspondence would mean that Z should be holomorphic. So even though we started out with a Noether theorem, that the only requirement is that you have the current which has both Z and Z bar component, which is conserved. But by additional constraint of two-dimensional conformal theory, we see that it actually satisfies a stronger condition that it is holomorphic. Okay? So if it is holomorphic, then we can consider some product of these operators, and the product should also be holomorphic. So you can ask, well, what this operator product look like. So we can actually begin to determine what these are. So for example, we do know that the commutation relation is given by this. This is required by combination of Noether theorem and Wigner theorem, as I said. And so that means the point. So QA is given by the spatial integral of the current, but now this is equal to the integral of Z component. Okay? So that means that this commutator is a contour integral of 2 of these, which goes into this. So this actually determines that JAZ, JBW must contain in the OPE a term like this. The simple pole in the OPE should be of this form. Okay, so that by contour integral it picks up the single residue and reproduce a commutation relation. There is also a possibility of having double pole, but the residue of the double pole has to be constant, because by the dimension analysis, this has dimension 1, 0, this has 1, 0. So it's natural that this has dimension 1, 0 because this gains additional dimension. But this has dimension 2. So that means that whatever that comes over here has to have dimension 0. But in unitary CFT, only dimension 0 operator is a constant. So you can only have constant. Okay? So this is called level of, and this structure is called Kac-Moody algebra. So this means that in the case of two-dimensional unitary conformal theory, if conformal theory has additional global symmetry of Lie group G or Lie algebra G, then it automatically implies that symmetry is actually bigger, that it has actually Kac-Moody symmetry. Just like in the case of Virasoro algebra, we can consider expanding this in terms of a mode expansion like this, then one can show that the commutation relation of Jn has this structure. So in mathematics literature, this is called Kac-Moody algebra. Where this delta AB is the Kashmir element, sorry, killing form, excuse me. The delta AB is the killing form of this Lie algebra. Okay, so it's a natural method in the Lie algebra, and if Lie group is compact semi-simple, then this is a positive definite method. Okay, so we have seen that whenever you have global symmetry in conformal field theory dictated by this Lie group G, then in fact there is a corresponding Kac-Moody algebra characterized by the level and the structure constant. Okay. In non-abelian theory, where FABC is non-trivial, then it turns out that consistency of the algebra and also the unitarity of the representation. Namely, if you have this kind of algebra, you can consider building highest weight representation, which is characterized by the condition that you start with the vacuum representation. So highest weight state, annihilated by n greater than 1, and then a build representation. Then if you want the representation space to have positive definite in a product, then a K has to be quantized. So if G is non-abelian, compact, then automatically implies that Z has to be integer, non-negative integer, actually positive integer. Okay, so that is required. So here I only looked at this left mover, but there is also corresponding structure on the right mover, and so in principle this level K can be different for left and right. I don't have time to discuss this, but this K is related to what's called chiral anomaly in the case of two dimension. For example, if you represent the J, so for example, if you have free fermion, then if there are n free fermions, then there is a symmetry that rotates these fermions, and that can become global symmetry. And in that case, these currents can be represented as bilinear of these fermions. J is expressed in terms of fermion, the wild fermion projected in one chirality. J bar is represented by fermions with another chirality. And since they involve the chiral projection, naturally they have chiral anomaly. And K and K bar for the right mover represent the chiral anomaly for these fermion algebra. And in particular, K plus K bar correspond to the K. So you sort of the K represent the left chiral anomaly, and K bar represent right chiral anomaly. Okay. So when I give the set of lecture on quantum field theory, this is one of the subjects I cover. Okay. So I'm doing this because heterotic string construction is a particular case of this, where group G is E8 or SO32. So this brings me to the following point, another point, which is how to construct this type of symmetry in string theory, in particular in heterotic string construction. So in the case of heterotic string, the object we use is a conformal field theory whose target space is a torus. So how do you construct this kind of non-abelian group structure out of torus is something I would like to discuss. And so in general, if you have this kind of Kac-Moody algebra, then of level K of group, then you can actually construct the energy momentum tensor or Virasoro algebra associated to, there is an energy momentum tensor associated to this Kac-Moody algebra, which can be expressed in this way: 1/2 of k plus what the notation I use, g, plus summation a goes to the Lie algebra JA JB delta AB. This has to be normal ordered, obviously, but essentially it's a bilinear of the current. Okay, so this is called the Sugawara form. So this is a Sugawara form of energy momentum tensor, which can play the role of energy momentum tensor for the current. So in particular, it satisfies this commutation relation, or this operator product expansion, z minus w squared 1 plus z minus w del w of JA of W. And so this is the correct operator product expansion algebra for the operator of dimension 1, 0.
Sorry,
You have a question?
What's the G in the denominator?
Yeah, so I'm going to explain. So I didn't explain. So G is a number. Yeah, I didn't explain. I'm sorry. G is a number called dual Coxeter number. Okay, and K is a level. So I'm going to tell you this, about these numbers. These plays important role. Okay, so in general, the total energy momentum tensor, if the conformal usually has this kind of symmetry, then the total energy momentum tensor is equal to this Sugawara energy momentum tensor and the rest of the energy momentum tensor, and the rest of the energy momentum tensor obviously commute with the group action. So the rest of the energy momentum tensor commute with J8. So you can sort of factorize the energy momentum tensor to Sugawara part and the rest. And this Sugawara part has, of course, operator product expansion by itself, which should give you the Virasoro algebra. Okay, and this central charge is given by the following formula: dimension of the group times k divided by k plus g. Okay, so this is something you can calculate by using this formula, and essentially using this operator product of j, you can derive these. Okay. So it's instructive to calculate the value of this central charge for some example. So let's do this in some example. So I wrote down some examples. So let's draw some table. Okay. So here is the dimension of G, and then there is a dual Coxeter number of G, and there is a C of G. And then let's, for simplicity, calculate this for k equal 1. Okay? And so let's start with A n. which is the same as SU n plus 1. So for SU n plus 1, the dimension is n plus 2. And the dual Coxeter number is n plus 1. So that means that C of this is equal to actually n for k equal 1. So I'm just calculating this for k equal 1. If you plug that over there, then this is what you get. So for for dn, which is SO2n, well, the dimension is n times 2n minus 1, and the dual Coxeter number is 2 minus 2, 2n minus 2. So again, C is equal to n. I'm doing this for AN, DN, and E and exceptional groups, E groups, because these are what's called has an important property called simply raised, which is going to be relevant for heterotic string construction. So I'm sort of anticipating this and just write. So in principle, you can work out all these examples. You can look at the table of Lie algebras, and then you can actually work out all these examples. And I think it's 30. And is it 30 or 90? Yeah. So this is 6, 7, 8. Okay. So in all the cases, the central charge when k is equal to 1 is the rank of the Lie group. So this is actually something very significant, and so I would like to explain what that is. But to do that, I need to remind you about the structure of Lie algebras. So I assume that you have taken most of you have taken undergraduate course on mathematical methods of physics, where you study construction of and representation of compact semi-simple Lie algebras. So Lie algebra G is a vector space, and its basis consists of two important categories. The one is the Cartan algebra. These are abelian and commute with each other. So you have Hi, Hj, and they all commute with each other. And these are called Cartan subalgebra. And the maximum number of Cartan subalgebra generator is actually the same as the rank. So this is where the rank comes in. So the rank is the same as the dimension of the Cartan subalgebra. So when you construct representation of Lie algebra, the natural basis that one should consider is eigenstate. So natural basis of representation space one consider are the eigenstate of H. Okay, and the rest of the generator, because you have a dimension of the group which is typically bigger than the rank. So that means that there are other operators, other generator of the Lie algebra. And you can choose the basis of these to be eigenstate of H themselves. So A, say for example, are other generators. Alpha, And you can choose this to be the eigenstate, right? Because you can also think the Lie algebras themselves makes adjoint representation of the Lie algebra generators themselves make adjoint representation. So you can choose to have eigenbasis of that algebra, and so then you can actually have this to be like that, where this have a vector. So these are called roots, and so alpha I is a root vector. Right? And okay, so therefore it's useful to classify the algebra in this way. So we can also use that basis for the Kac-Moody algebra. So what would happen if you do that? What would happen if you do that? Well, so that means that the Kac-Moody algebra has a natural basis where you have Ji which are abelian. So therefore you can have just this operator product expansion where I, J goes from 1 to n, and these are Cartan subalgebra. Okay? And then you can have root vectors. So you have J alpha of W, which goes like Z minus W of alpha of what was the notation I used? Alpha of I of J alpha. Okay, so you can organize the algebra in this way, and you also have OPE of alpha with itself, the root with itself, which I don't write down. But you can also write J alpha of Z, J beta of W to be something that you can easily figure out. So here I assume that K equal 1. Okay. In general, there is a K over here, but I wrote this for K equal 1. Now, interesting thing is that when K equal 1, the central charge, at least for SUN, SO2N, and E series of Lie algebras, central charge is n, which is the same as the number of Cartan subalgebra. So what this seems to be strongly suggesting is that in this case, Lie algebra, the Kac-Moody Lie algebra can be realized in terms of n free bosons. So this is the same as central charge of n free bosons. So this is the central charge of n free bosons. And you can consider writing J to be called I of del Z of phi I, where I go from 1 to n. Okay, so you can consider expressing this in this way. And you can actually show that in this case, J alpha is expressed in terms of E of I of Ji phi I, essentially, with the appropriate normalization factor in front. You can show that if you do that, then this satisfies the correct operator product expansion. So essentially, you can have this kind of structure. Okay, and simply raised means that these vector alpha, these are called root vectors, all have the same length. And it is normalized so that this actually also have conformal dimension 1, 0. Obviously, this has 1, 0 too. So these all are entitled to be current. Okay. So this is the construction. We have already encountered a simple situation of this in the one of the first lecture, which is C equal 1 free boson at the self-dual radius. R is equal to square root of 2. So there we have seen that so this is the moduli space of R, where this is R is equal to square root of 2. Okay, so remember that we have this duality, T-duality transformation. So the radius can be restricted to be greater than square root of 2. And at the end point of this moduli space, something special happens. And that something special is that you can have actually SU3 algebra. Plus minus is equal to e to the plus minus I square root of 2 times 1. And this realizes the SU2 Kac-Moody algebra. Okay? So, so this basically generalizes this for AN, DN, and E series. Okay? So heterotic string construction take advantage of this one, because E8 in particular is a very special case where you can only use left mover to realize the algebra. So for example, this case is you cannot separate out the left mover only, because the conformal field theory we are considering here has both left mover and right mover. So the algebra we have is actually SU2 left times SU2 right. And if you calculate the partition function in this theory, it's actually sum of product of left holomorphic and anti-holomorphic object, and it does not completely factorize this. The E8 Kac-Moody algebra is very special in that it factorizes, and this is very important for the following reason. Okay, so we have seen that if you have Lie algebra G, we might consider this vertex operator, or this is called vertex operator construction, of the algebra where J, so these are Cartan, and then there is a root vector which is e to the I alpha I phi I summed over I, so these are roots. Okay, and so this generates the Kac-Moody Lie algebra, I said. But this suggests that there is actually a natural torus, which is a t-dimensional torus, which is given by n-dimensional Euclidean space divided by some lattice. And that lattice should be generated by this root vector, because that's, if you consider this kind of torus, then this type of operator automatically appears as a momentum and winding. So this, what you have over here, are momentum and winding number of the. So if you consider conformal to Euclidean torus, then there is a momentum and winding number, and this alpha represents the momentum and winding number. But but if you want the CFT to have a purely left moving sector, then lambda has to be even and self-dual and Euclidean. And this is actually what we want, because remember that we are considering heterotic string construction. So in heterotic string, what we were doing was to combine the bosonic string and superstring. So bosonic string has 26 dimensions, and the superstring has 10 dimensions. So this is for the left, and this is for the right. So the idea was to replace this by 10 flat dimensions for the left mover times the 16-dimensional torus. And regard this as a 10-dimensional space-time and use this to generate some group. In particular, SO32 or E8 cross E8 gauge group. But you see that you only have left mover, and you don't have right mover. In general, if you consider conformal theory on the torus given by dividing flat Euclidean space by Euclidean lattice, then it has winding number and momentum. And for example, in the case of circle compactification, remember that we have this formula that H is equal to 1/2 of P left square plus the number of excitations, where P left is equal to M over R plus NR. And then H bar is equal to 1/2 of P right square plus N right, where P right is equal to R over M minus MR. So in general, if you have winding and momentum, you have both left mover and right mover with non-trivial conformal dimensions. You cannot decouple them. But there are special things. Special things happens when this lattice is even and self-dual, in which case actually this lattice structure factorizes, and you can actually extract only the left moving part. This exists only when n is equal to 0 mod 8. So that's why we couldn't do that in one-dimensional torus, because 1 is not 0 mod 8. So it exists only when the dimension is equal to 8 or 16 and 32, etc. 24 and 32, etc. And so the first dimension that appears is 8. So let's first look at the 8th dimension. So in 8th dimension, there is actually a unique even self-dual lattice. And 8th dimension, there is a unique even self-dual lattice, and this is generated by 8 generators. And this is called E8 lattice. And this is related to this one. So that's essentially why E8 cross E8 construction is possible. Basically, you make 2 copies of this. And so one of the ideas of constructing E8 is actually the following, that E8 has a subgroup SO16. So you can consider constructing root lattice of SO16 and augment it with some additional root generator to construct E8. So O16 is easy because the root vector of orthogonal group is just of this type. So there are 8 dimensions, so there are six of them and 1 minus 1. and then you just shift it like that, and then you have E7, which is 0, 0, all the way to 1 minus 1. So if you have this together with Cartan subalgebra generate the Lie algebra of SO16. Okay, so we just need to add one more thing, which is E8, which is 1/2, 1/2, all the way to 1/2. Okay, so this happens only in 8 dimensions. This is very special. The fact that you can add this and make self-dual, even self-dual lattice is only possible in 8 dimensions for the following reason. So conformal dimension, so even means that the lengths of these are all even. So for example, if you consider E1 square, this is 1 plus 1, so this is 2, right? And but how about this one? Well, so there is if you consider E8 square, E8 dot E8, well, this is there's 1/2 square, but there are 8 of them. So this is actually 2. So, but this is it's important. This is 8, so that the length of this is still 2. So it only happens in 8 dimensions. Okay. So so there is SO16. So this is SO16. This generates SO16, and what this is actually this is actually the one of the weight vectors of the spinor representation. So where is my note? Yes. Yeah, that's good. So this is actually spinor. The weight vector of spinor representation of SO16. And if you include that and consider these as the positive roots, then it's actually complete the E8 root. So in some sense, it's very much like supersymmetry. It's very similar to supersymmetry, namely that you have you in addition to adjoint representation, you add spinor representation of rotation group in 16 dimension, and then that enhances to E8. Okay. So then E8 lattice is basically generated by this, and then we can actually calculate the Paschen function of this space, and so this is T8. So the space of R8 divided by lambda of E8. So this is equal to the eta function raised to the power of 8 times theta function associated to the E8 lattice, where theta function associated to E8 lattice is defined to be a sum of vector belonging to E8 of Q to the momentum square. That vector square, where the vector square is calculated using the natural metric on this lattice space, where this is degenerated as integer linear combination of this. Okay. In terms of so this form suggests that these are generated by these vectors phi I, and then E alpha, where alpha goes to 1 to 7, are equal to E of plus minus phi I alpha plus alpha minus I phi alpha plus 1, I think, if my counting is correct. And E of E8 is equal to E of 1/2 of I plus minus phi 1 plus minus phi 2 plus minus phi 3, etc. Okay, so this generates the Katsumudi. So you can check that this generates the Katsumudi algebra of E8. So this is E8 Katsumudi. Okay. So you can calculate this, and because your lattice sum is explicitly written, so we can actually do this calculation. So, but then there is one more miracle that takes place, which is actually very nice, and which is the following. So we can calculate this E8 partial function in terms of 8 to the 8 and the E8 lattice calculation. So you sum over these momentum. But then you actually find that you can actually write this as 1/2 of q to the minus 1/3 times n equal 1 to infinity of 1 plus q to the n minus 1/2, 16, plus n equal 1 to infinity of 1 minus q to the n minus 16, 1 minus 1/2 to the 16, plus 2 to the 8, product of n equal 1 to infinity, 1 plus q to the n of 16. Okay, so you can also write it, rewrite by using simple, well-known formula for the relation between relation for the theta function, elliptic theta function. You can rewrite this sum over E8 lattice in terms of sum of 3 terms, each are infinite product. But this is rather miraculous because this formula is very natural because you have 8 free bosons. So this is a Bose-Einstein partial function, and this is momentum sum. But these are numerators. And this has a form of Fermi-Dirac statistics. So again, there are fermions. So what's going on? Well, what's going on, you can see this from this construction. So we just noticed that E8 lattice, E8 Katsumudi vector can be written in this way. So let me write it out. So we saw that the Ji is equal to I of del of phi I, and J of E of alpha, where alpha is 1 to 7, are equal to E to the plus minus I, plus of I phi alpha, minus of I phi alpha plus 1, and then J of E8 is equal to E to the 1/2 of I plus minus phi 1 plus minus phi 2 all the way to plus minus phi 8. Right? Now look at this, and then this should remind you of something, which is like there is a Bose-Fermi correspondence. Or bosonization of fermion, which we used when we talked about the supersymmetry. But the bosonization formula or fermionization, in this case, they are to be proper. That for each phi, we can consider psi I, which is equal to E to the plus I phi I, and psi bar I, which is E to the minus I phi I. These do not exist in the Hilbert space. These do not exist in Hilbert space, but if you naively count the conformal dimension, this has conformal dimension H is equal to 1/2. These do not appear in the Hilbert space, but their pair appears in the Hilbert space, because you can write this as psi alpha plus 1 bar, for example. Right? So namely that this is actually a pair of fermions. And and then you can think of this as a spin operator. So remember that if you have fermions, you have to choose whether these fermions are in Raman boundary conditions or Neubel-Schwarz boundary conditions. And there's an operator called the spin operator which interpolates between Neubel-Schwarz ground state and Raman ground state. If you act spin operator in Neubel-Schwarz ground state, it maps the Neubel-Schwarz sector to Raman sector. And this operator does the exact result because of the exponent is 1/2. So if you calculate OP of this operator with this operator, there is a branch cut. Okay, and so this is a spin operator which maps NS ground state to Raman ground state. And so therefore, yeah. So and then another important point I would like to make is that there are 8 of them, right? Because I goes from 1 to 8. But these are complex fermions. So that means that there are 16 real Majorana wire fermions, and they are all massless. So that means that there is actually SO16 acting as a vector field, vector representation on fermions. So these are representation of 16. Because you can decompose 8 complex fermions into 16 Majorana wire fermions, and there is manifest SO16 symmetry in these fermions. And then this one, sigmas, represent the spinor representation. So this is so what is this? There are 2 to the 8 states. These are spinor representation. Okay, and these spinor representation. And you can see that these 3 terms correspond to these spinor representations. And you have this because you have basically you have fermions with a projection operator, the chiral projection. So that you have this -1 to the -1 to the f. So that you extract the fermion number. So I should say -1 to the f. So the p is equal to 1/2 of 1 plus. Okay, and these are spinor representations. Okay, and then there's 1/2. Because these are so if you have if in 16 dimensions, so if you have all 16, if you have spinor, you have 2 to the 8. But irreducible representation requires that you do the wire projection. So you have to divide this by 1/2. And in fact, there is 1/2 here. So here you are projecting onto. So you start with this 16 fermion, and you project it onto even fermion number sector. And here you have 2 to the 8 divided by 1/2, which means that we are considering chiral spinor representation. Okay, so there are alternative representation of E8 representation. Both in terms of bosons, which is living on torus. So let me write it over here. So that means that E8 can be realized. 8 can be realized by holomorphic boson phi I on T8, which is R8 divided by E8 lattice, or a chiral fermion psi I representing, and then there are actually 8 of them. So there are 8 of them, and representing the SO16 symmetry. And then combining this bilinear chiral fermion together with the spinor representations also realizes E8 symmetry. This is very much like supersymmetry, except that here these are both bosonic generators. In supersymmetry case, you have bosonic generator and fermionic generator, but in E8 case, the spinor representation of the rotation group are also in bosonic generators, and these provide additional generator needed to enhance SO16 to E8. Okay, so this E8 part of the heterotic string has this type of construction. Okay. Now, so this was the most sort of difficult part, and once we got through this, the rest is easy. It's actually very interesting to see how actually E8, the SO16, the vector, the adjoint representation of SO16, together with the spinor combines into the E8 representation. But that's I think you can figure it out. It's explained in my lecture note too. So adjoint representation of SO32, of SO16, there are 120 generators, and then spinor of SO16 has 128, which is 2 to the 8 divided by 2. And so if you sum them, you have 248, which is a dimension of adjoint representation of E8. Okay, and then the way that it turns out is rather interesting, but I leave it to your exercise to see that. Okay. So now, given this, the rest is very easy. So if we want a full heterotic string, then we can do the same game for the lambda E8 plus E8 or lambda SO32, and these are unique choices in 16 dimensions. So we can see that up to these there are 2 even self-dual lattices in 16 dimensions. Modulo SO16 rotation. So modulo SO16 rotation, there are 2 types of representations, and E8 cross E8. But if you calculate the partition function, they turned out to be identical. So if you just look at the spectrum, you can distinguish them, although they have different symmetry assignment. And excuse me. And then this is given by formula which is very similar, which is the following things. Well, first of all, you can write it as a product of 2 things. So that is actually a very interesting identity. So let me write it out. So Z of E8 cross E8 is basically the free boson on R16 divided by lambda E8 cross E8. But this is actually, of course, it's not, there is no mystery to it. It's just a product of two partial functions. So you just square this thing, right? So in the case of SO32, you have you do something very similar, which is now you consider 32 free fermions, and then you sum over NS and Ramon sector, and then do the fermion number projection. So it's exactly the same structure as this one. Okay, and interesting thing is that so this one contains 8 of these factors, 16 of these factors, and and then there are 3 of them, and so you take square, and there are 9 terms, and somehow these 9 terms recombine into some of these 3 terms, and showing that these partial functions are unique. Now, this looks very mysterious, but a priori, this is something we could have expected for the following reasons. A priori, we know that if the lattice is even self-dual, then if you consider corresponding torus and calculate this holomorphic partial function, it's automatically fully modular invariant. Namely, it is invariant, both are invariant under SL2Z. What it means is that if we consider A, B, C, D, which are elements of SL2Z, then it is invariant under A tau plus B, C tau plus D. Okay? So it's fully modular invariant, both of them, because both come from even self-dual lattice. But mathematics tells us that there aren't so many fully modular invariant holomorphic objects. They are very rare. And in particular, in this dimension, they are essentially unique with this leading property of the Q expander. So that automatically tells you that if you have 2 independent constructions, they should coincide. You can check that the normalization for the first few terms, and if they agree, then the rest should agree. So that's sort of the easiest way to check that these are the same. So it just follows from the fact that there aren't so many of these things in holomorphic things. That basically means that heterotic string constructions are very rigid. That in order to do this type of construction, you have to maintain the modular invariance, and if you want this combination of superstring and heterotic the bosonic string to maintain modular invariance, you need to choose this 16-dimensional torus to give you a partial function which is fully modular invariant, and that requires this torus to be associated to the even self-dual lattice. Okay, so that's the construction, and so let's use this to understand what kind of theory you obtain in 10 dimensions. Okay, so the heterotic string now. So for the left mover, we have R10 times T16, which is equal to R16 divided by lambda E8 cross E8, or SO32. And then for the right mover, we have R10. And for here we use the bosonic string. So here we use the bosonic string. So that means that the ground state is tachyon. And then there is a first excited state, which is generated by del x mu, where mu goes from 0, 1 to 9, which corresponds to the 10 dimension. And then there are, so this operator has conformal dimension 1, 0. But there are other ways to generate operator 1, 0, which is to use a Kac-Moody generator of E8 cross E8 or SO32. So you can have JA, where A is either E8 cross E8 or SO32 generators. So you have these choices. Okay, in the case of superstring, in the case of right mover, you have a superstring. So therefore, you have NS sector or Ramon sector. Sorry, NS sector or Ramon sector. Excuse me. So NS sector has a spinner, the worldsheet spinner, which is a vector in 10 dimension, and then there is a spin operator which generates the Ramon sector. So these are spinner, and then these are Majorana wire spinner in 10 dimension. Okay, so basically what you do is, so these are left mover. These are left mover, and these are right mover. Okay, and then you combine them to construct physical spectrum. So let's look at the massless spectrum. Okay, so as I said, the ground state of bosonic string has tachyon, but ground state of superstring has no tachyon, and the level matching condition requires therefore that state without the same mass level for the left and right should be projected out. So therefore, this automatically removes tachyon, as it should, because supersymmetric theory should not have tachyon in it. So that's consistent. So we can look at the massless sector. So for massless sector, as I said, the left mover is either a vector or a scalar in adjoint representation of E8 cross E8 or SO32. These are vector in singlet representation of this group. So left mover has heterotic string. The left mover has E8 cross E8 or SO32 lattice structure. So in principle, state generated in the left mover can be representation of E8 cross E8 or SO32, but this one is invariant on the SO32. It's excitation on 10-dimensional side. So these are singlet of this symmetry. But in addition, there are adjoint representation of this symmetry. So how about the right mover? So right movers are in vector in 10 dimension, or spinner, Majorana wire spinner in 10 dimension, and they make supersymmetry. Okay. So we can see that. So we can now combine left mover and right mover and see what kind of state you get. Well, for example, if we choose this vector and if you choose this vector, it's a bivector. So you can symmetrize or unsymmetrize. if you symmetrize it, you have massless spin 2 operator. And by Weinberg theorem, that must be graviton. Because Weinberg theorem says that if you have spin 2 massless operator particle, then it should be graviton. So you have graviton in it, but you also have unsymmetric tensor in it. So, and then a scalar, which is dilaton. So this and then there is a spinner related by supersymmetry. So this gives rise to n equal 1 supergravity. It's called n equal 1 because this is a minimum amount of supersymmetry you can construct in 10 dimensions. So supercharge in this case maps vector into Majorana wire spinner. So the spinner, the spinner supercharge in this case is themselves a Majorana wire spinner. And so if you have single Majorana wire spinner as fermionic generator, that's the smallest supersymmetry you can have. So it's called n equal 1 supergravity. By the way, in contrast, when we talked about type 2A or type 2B, we had a supersymmetry for both left mover and right mover. So these are called n equal 2 supersymmetry, supergravity in 4 dimensions, and 10 dimensions. And then, in fact, there are 2 types of n equal 2 supergravity in 4 dimensions because supercharges, as I said, the Majorana Y. But when you say Y, well, you can have 2 choices, whether you have the same chirality for the 2 supercharges or opposite chirality. And if 2 supercharges have opposite chirality, these are called type 2A, whereas if they have same chirality, these are called type 2B. So we have now seen that there are 3 types of supergravity in 10 dimensions. N equal 1 supergravity coming from heterotic string, and then n equal 2A, or 2B supergravity coming from closed superstring. How about this one? Well, if you choose this one, then the left mover is a scalar in space-time rotation, but in the adjoint representation of E8 cross E8. And right moving excitation gives you a massless vector. But these are gluons. These are the vector field, because these are vector taking value in adjoint representation. And then there's a corresponding spinner. So you also have spinner, which is in adjoint representation. So you may call it as gluino or gaugino. So then you have n equal 1 super Yang-Mills theory. In for E8 cross E8 or SO32. So the massless sector of a heterotic string, therefore, is n equal 1 supergravity coupled to n equal 1 super Yang-Mills theory with this particular gauge group. So in fact, this is one of the work that Michael Green and John Schwartz did in the summer of 1984, that they show that in general, if you consider n equals 1 supergravity coupled to super Yang-Mills, this theory suffers from gravitational and gauge anomalies. And because these are chiral series, because these are Majorana wire spinner, so in general, they can have gauge anomalies and gravitational anomalies. But they discovered that if you choose a particular gauge group, which is E8 cross E8 and SO32, important thing was that they have the same dimensions. And then the anomaly cancels. And so that was sort of motivation of heterotic string construction. Because the SO32 gauge group can be realized in open superstring theory, but E8 cross E8 was not possible. But heterotic string made it possible to construct. Okay, so that's the construction of heterotic string. So I still have about 8 minutes. So let me mention one important generalization of heterotic string construction. And then in the next lecture, I saw that there are 4 groups signed up for the final project. 1 for the next Monday and 3 for the next Wednesday. The last time I checked, it was like that. So that means that each group can get about half an hour, a little bit less than that if we want to finish 5 minutes before the 10:30. But we need to leave some time for questions. So maybe you should aim at presenting 20 to 25 minutes each. But that means that on Monday we still have about an hour for lecture. So I plan to discuss beginning of orbifold construction because well, we are still in 10 dimension, but we don't live in 10 dimensions, so we have to figure out how to compactify the extra dimension to generate 4-dimensional space-time, and then I would like to explain how you get how you begin to get standard model of particle physics from there. So I would like to start discussing that. But let me first discuss a simple way to compactify it, which is to compactify heterotic string further on the torus. So we started out with heterotic string. On R10 times T16. So this is where we started out with. And 16 was sort of an important choice for two reasons. One was that 10 plus 16 is 26, which is a critical dimension of bosonic string, and 10 is a critical dimension of superstring. So 16 is the difference of these two critical dimensions. But another thing was that the even cell dual lattice was possible in 16 dimensions. So even cell dual lattice is important for the heterotic string construction, and that's only possible for dimension 0 mod 8. Okay, so that was a choice that one could make, and but you can consider generalizing it. In the following way, that we could consider generalizing it by further compactifying this to d dimension. So that you can have a lower number of flat dimensions. And if you compactify this on torus, why not in fact combine them to make a single torus? So you can imagine having this type of torus construction. So the question is that so if you want to do that, what's the most general thing you can do to realize that? So you can think of this in the following way. So T16 is R16 divided by lattice. But this was acting only on the left mover. The right mover was entirely living in 10 dimensions. But if you want to compactify this further to d dimension, part of that contains the right mover also. So namely that now in this d of 16 dimension, you can have actually d-dimensional right mover, and then d plus 16 dimension left mover. So previously we only had 16 dimension left mover, but now we have d dimension right mover and 16 dimension left mover. Excuse me. And correspondingly, you have this momentum, left moving momentum and right moving momentum, which lives on the lattice. These are combination of momentum and winding number, just like in the case of circle compactification. And this lives on the lattice of signature. So there are d plus 16 dimensional momentum living on d plus 16 dimension on the right mover, and d dimension in 16 dimensions. Okay. So the left and right moving momentum therefore lives in this dimension. Okay. So the question is, well, so what are the constraints? What are the constraints? So this was figured out by Narayan. And so the requirement is that that this makes lattice. So the lattice generated by this momentum and winding. So you take value in all these dimensions. Has to be so that it is even and self-dual. But not with respect to the Euclidean metric, but indefinite metric. To the metric P left, P times P prime is equal to P left prime minus P right prime. Namely that you consider space of signature D plus 16 and D. And then it's in this indefinite signature. It's actually easy to understand why this is required, because if you have this space, then the Paschen function involves summation of P left and P right over this lattice of Q to the 1/2 of P left square, Q bar to the 1/2 of P right square. But then if you do one of the modular transformation of tau to 2 pi I tau, then this I guess there is no 1/2 here, probably. This is equal to, this gives rise to the phase exponential of 2 pi I of P left, actually there is 1/2, excuse me. Pi I of P left square minus P right square multiplied by Q to some power, the original power. And so in order for this to be modular invariant, it is necessary that this is 1. And this requires that P left square minus P right square is an even integer. And so that's sort of the origin of this even, with respect to this indefinite signature. In general, you can actually ask, well, what if you consider more general dimension, D prime and D? And you can actually show that, so D left and D right, you can show that the even self-dual lattice exists only when the difference of the two dimensions are 0 mod 8. And so this was what figured out by Narayan, called Narayan compactification. And the heterotic string is special case of this where this D is equal to 0. So maybe in the next lecture I'll briefly talk about the heterotic Narayan compactification, and then discuss a simple example of orbifold construction. And that is a lecture for this quarter, and then next quarter we'll discuss Calabi-Yau compactification and deeper. Okay, so that's it for today. Thank you.